Good evening, everyone. Welcome to Boise State Physics First Friday Astronomy. My name is Heidi Wu. I am an astronomer and assistant professor in the physics department of Boise State. Before we get started, I have a few announcements. We have a very exciting lineup for spring 2022. So I'm going to share my screen for. Oops, Brian, can you allow me to co-host me? Yes. In January, we will have Chris Anderson from College of Southern Idaho. He'll tell us about In the Shadows of Asteroids, Stellar Occultation. And in February, we will have Professor Yuan Li from University of Northern Texas. She'll be telling us turbulence in the heavens. In March, we will have Dr. Carl Schmidt from Boston University telling us about Io's atmosphere and the plasma torus. And in April 1st, we will have Dr. Aaron Cox from Sierra Northwestern University and telling us about a stellar clock, how to build a planet. And we expect the event to be both in person and live stream. So please join us in spring 2022. Today, I'm very excited to be joined by Tyler Gordon. Tyler Gordon was an undergraduate student at Boise State, and we are all so proud of him. And I'm actually not going to be able to take credit because I wasn't here when he was a student here. And Tyler started his PhD in University of Washington in 2016. And in this past few years, he has really impressive publications and as well as experiences in teaching and outreach. And he has been a planetarian coordinator in University of Washington and also organized the Astronomy on Tap in Seattle. And today he'll be telling us about his very exciting research on exomoons and planets. Thank you, Tyler.
All right. Hi, everybody. I'm just going to go ahead and try to share my screen real quick. Okay, so is that showing up?
Looks great.
Okay, great. So yeah, as Heidi said, my name's Tyler Gordon. I'm a graduate student at the University of Washington and a graduate of the physics program there at Boise State. And so today I'm going to be talking about the search for exomoons. And I guess to start off, I should just let you all know what an exomoon is. It's nothing too complicated. An exomoon is just the moon of an exoplanet. So any planet orbiting a star other than the sun that has a moon, that moon we would refer to as an exomoon. So that's all that word means. So in the past 20 or 30 years since we've been discovering planets around other stars, we've confirmed the detection of over 4,500 of these objects. And in all that time, we've detected exactly 0 exomoons. So what I want to talk about today is I want to talk about, for instance, like why in all that time, why haven't we detected a single exomoon? Is it because there aren't any exomoons out there? I think the answer to that pretty simply is no, it's not because there's no exomoons out there. And I think you can see that mainly just by looking at our own solar system. So this is a graphic showing the planetary and the satellites, or at least some of the satellites of the planets in our own solar system. So in addition to the gas giants that you see here around the edge of the graphic and the terrestrial or rocky planets, our solar system has a number of moons, some of them very large. So down in the bottom left here are the moons of Jupiter. The largest of those, Ganymede, is larger than Mercury. Earth has a pretty good sized moon. Saturn has its moon Titan, which is up here near the top, which is large enough to hold onto an atmosphere. So in our own solar system, we see lots and lots of these objects. We also have every reason to expect from like planetary formation models and simulations of planets forming around stars that it should be easy to form moons in those scenarios as well. So there's like 3 questions that I want to answer with this talk. The first of those is, why are we so interested in searching for exomoons to begin with? And if they do exist, then why haven't we found them yet? And finally, I want to talk about how I think that exomoons can be detected in the future with future observatories and future instruments. So to expand on what makes exomoons worth searching for, I think the first thing that makes them a really valuable target is that they're part of the complete picture of an exoplanetary system. So to illustrate this, I just have down here a graphic showing the TRAPPIST-1 system. So this is a M dwarf, a very low mass star that hosts 7 terrestrial worlds around it in pretty compact orbits, not quite as compact as this graphic would seem to suggest. This is not in any sense to scale. But this is a really interesting system, but we know a lot about this system. We've observed this system a lot. One thing we don't know is whether there are any moons in a system like this. We don't really even know whether moons could exist in a system like this, if their orbits would be stable, or if the proximity of the planets and any migration that those planets went through would cause the orbits of exomoons to become unstable. So in order to form a complete picture of a very interesting system like TRAPPIST-1 or any other exoplanet system, we need to understand whether there's moons present in that system and what kind of moons might be present. I think the second thing that makes exomoons worth searching for is that they help us understand our own solar system. So up here in the top right of this slide, I have Jupiter and its 4 Galilean moons, the largest moons of Jupiter. And the thing to notice about these moons is that they're all sort of roughly the same size. So in this system of moons, the total satellite mass of Jupiter is kind of spread out pretty evenly between these 4 bodies. And that's really different than what we see in the Saturn system of satellites. And so that's down in the bottom left. This largest object here is not Saturn, that's actually Titan, the moon of Saturn. It looks fuzzy like a gas giant because it has a thick atmosphere. So that's a very large moon. And then all of the other moons of Saturn are quite a bit smaller in comparison. So in contrast to the Jupiter system of satellites, around Saturn, we have all of the satellite mass pretty much concentrated in just one object. And the rest of the satellites of Saturn just kind of pick up the crumbs. And we don't understand why that is. So this is an area where observing systems of exomoons around planets, around other stars, can help us understand why these different formation scenarios happen in our own solar system. This is also by far not the only mystery about moons in our own solar system that exomoon observations could help us answer. So for instance, the Earth's moon is thought to have been formed by a massive collision between the Earth and another planetary body early in the history of the solar system that flung material out into orbit around the Earth that then coalesced back into the moon. And that seems, to me at least, like a pretty unlikely occurrence. So one thing that we might be curious about is whether that kind of process can happen in other solar systems and how common that actually is, or if what we see here in our solar system might actually be rare in that respect. And there's a number of other mysteries about moons in our own solar system that I think we could really go a long ways towards answering by being able to observe moons in other solar systems. And finally, and I think this is maybe one of the most exciting things about exomoons, is that they might actually be habitable worlds in their own right. So in our own solar system, we have icy moons of outer planets that are far outside of the habitable zone being sort of the range of distances from the sun in our solar system where liquid water can exist. So these moons are far outside of that, but they maintain liquid water under their icy crusts, and they're able to maintain that liquid water because they experience tidal forces as they orbit their gas giants. So Europa here in the bottom left orbits Jupiter, and Enceladus in the top right orbits Saturn. Those tidal forces that they experience heat the interior of the moon and provide a source of energy besides solar radiation that can actually keep water liquid. And where there's water, we think that means that there's a possibility, at least one of the ingredients for life is in place there. So when we look to extrasolar systems, we often think of like rocky planets in the habitable zone as the only place to look for life. But I would argue that we could consider gas giants outside of the habitable zone that host large exomoons to also be potential places where life could form in an exoplanetary system. And in addition to that, a massive exomoon around a gas giant in the habitable zone, if it's big enough to hold on to an atmosphere, could be habitable in that sense as well. So those are just some of the reasons that I think exomoons are a really exciting target to search for. Now I want to talk about why, if they're so interesting, why haven't we found any of them yet? And I think the simple answer to that question is that it's because they're rare, or at least exomoons that are large enough to be detectable with our current instruments, with our current telescopes, are rare enough that we haven't happened to find one yet. And there might be many, many more exomoons that are too small for us to detect, but it'll take new instrumentation, new methods of analyzing data from those instruments to be able to detect those smaller moons. So in order to sort of expand on why it is that our current methods aren't good enough to detect exomoons, I have to talk first about some of the methods that we use to detect exoplanets, because those are the same ways that we would hope to detect exomoons, maybe with some slight modifications. So the first of those that I want to talk about is called direct imaging. This is probably one of the most sort of conceptually simple ways to detect an exoplanet. This is where you just take a picture of the star and you see planets around it. Now, on a technical level, it's a bit more complicated than that because stars are very, very bright and planets are very, very dim, typically. So what you have to do is block out the light from the star with what's called a coronagraph. And that's what you see here. And the black circle in the middle of this image is the coronagraph blocking out the light from the star. Around that, you see an interference pattern. And that's just created when you block the star's light, you get an interference pattern around the edges of whatever's blocking the light. And then you see orbiting around that, the planets. And those planets are bright planets. So you can only do this for systems where the planets are bright. They're giving off enough light to be detected by the telescope. And so that usually means that we're limiting ourselves to systems where the planets are young, where they're relatively newly formed and they're still emitting some of the heat from their initial formation. And so this is a method that's great for bright planets that are far from their star, and far from their star because you see the interference pattern here would make it very difficult to see a planet that was too close to the edge of that coronagraph. And this is a bit of a problem for detecting exomoons via a method like this, because exomoons are likely to be dim because they're small, and because they're small, they would radiate away the heat from their formation a lot faster. So they wouldn't be giving off as much light as the planets in this image. And then the other problem is that moons orbit close to planets, and you see that the planets in this picture aren't perfect little points, they're actually bright disks. And so you would have to disentangle the signal of the moon from that of the planet. It's sort of the same problem you have with detecting the planets at all in the presence of the star. So there's some sort of big technical limitations there that you'd have to overcome in order to detect exoplanets by this method. And in fact, I don't think anybody has really suggested detecting exomoons this way. Sorry, exomoons, not exoplanets, because it's just a little bit too hard for the foreseeable future. Now I want to talk a little bit about radial velocities, and then I'll show you how we might be able to combine radial velocities with the direct detection technique in order to detect exomoons. So I have a neat graphic here from Melissa Obertus showing how radial velocities work. It's a very cool graphic, but there's a lot going on. So I'm going to try to tackle it sort of piece by piece for you. In the top left of this graphic, you see kind of a top-down view of a planet orbiting a star. And what happens when a planet orbits a star is that the star doesn't stay perfectly in place. The star actually wobbles back and forth under the gravitational influence of the planet, just like the planet moves under the influence of the star. And so if you look below that at the bottom left, you see an edge-on view of this system showing the star wobbling back and forth. But in addition to wobbling back and forth, because it's on a circular track, it's also moving towards and away from us. And it's that towards and away from us motion, which we call radial motion, and that's where radial velocity comes from. That's what we can actually detect. And we detect that via the Doppler effect. And the Doppler effect is the shifting of light to shorter wavelengths as the object moves towards us, and then longer wavelengths as the object moves away from us. So that's what we see on the bottom right of this diagram, is a little a drawing of a spectrum like you might see from a star. And it has little dashed lines in it that are staying constant. And those dashed lines represent the known locations in the spectrum of absorption lines. So those are specific wavelengths at which light is absorbed by material in the outer layers of the star. And we know what those are because we can go into a lab and play around with different elements and see where their absorption lines lie. The solid lines that you see moving back and forth, that's simulating what you would see when you actually observed the spectrum of this star. When the spectrum is blue shifted as the star is moving towards us, those lines move to the right. And then when it's shifting away from us, they move back to the left. And so we can use that to measure the velocity of the star towards and away from us, which tells us that there's a planet present around that star and something about its orbit and its mass. Now, what we can do potentially is combine these things. So we can take this direct image and we can isolate the light from one of these planets and observe the spectrum of that planet. And then we can do this radial velocity analysis like we would on a star to discover an exoplanet. We can do that for the exoplanet in order to attempt to detect a moon around it. And that's actually been tried. So this is a very recent paper by Vanderberg and Rodriguez that came out just this year, looking at this same system, HR 8799, and for 3 of the planets trying to do just what I said, trying to detect radial velocity variations in the spectra of the planets. And so on the y-axis here is the radial velocity for each of those planets. On the x-axis is time. So these have been monitored for over a decade at this point. It may not be obvious just looking at this, but the takeaway from this paper is essentially that this is a null result. These radial velocities that they've measured are consistent with no back and forth movement on the part of the planets at all. But when you detect nothing, when you get a null result, you don't just wash your hands and walk away. You can do something with that. And what you can do with that is place limits on your ability to detect things. So you can say, all right, given that we didn't find any moons, what kind of moons could exist in this system that are just too small or on the wrong orbits for us to detect? So that's what they did. And I'm just showing you one of the plots from the paper. This is for the planet C, HR 8799C. On the x-axis here, you have the mass of a planet. It actually says minimum mass, and I'll explain what that means in a second. But for now, you can just take that to be the mass, sorry, not of the planet, of a potential exomoon in this system. And on the x-axis, you have the orbital period of, again, a potential exomoon around this planet. And these purple lines that they have are contours that show confidence intervals for the detection. Just to make this a little bit simpler, I drew a black line on here. And I'm going to say that that's sort of the sum of all these confidence intervals. So anything above this, any exomoon above that black line would have been detectable by this method, very likely. And any exomoon below that line would not be able to be detected even if it existed in that system. So these are exomoons that could still exist around these planets, and we wouldn't have seen them in this analysis. And I think the thing to note here is that, so if we go out to a period of say 5 days, and look at where this line lies, it lies, if we track that over to the x-axis, that's at about 1 Jupiter mass. So what they're saying here is that for a 5-day orbital period, you could fit a moon with the mass of Jupiter around that planet and still have it be undetectable. And anything with the mass of Jupiter, I would say, is probably not even a moon, right? So that encompasses basically any moon that could exist around that planet. As you go to shorter periods, that gets a little bit better. Maybe you could detect smaller moons, maybe down to the size of the Earth. But I think the takeaway here is that this is a really weak constraint on the presence of moons in this system. So this is really more of a proof of concept. It's not something that was ever likely to detect exomoons, but I think it's a really cool proof of concept. And towards the end of the presentation, I'll talk about how I think this might be a path towards discovering exomoons in the future. I'll just real quickly add that the reason this says minimum mass on the y-axis is because this is sort of for the best case scenario. This is the scenario where you have a moon oriented in such a way that it's causing the maximum possible radial motion in the planet. If the moon's orbit is oriented any way other than that perfect angle, straight edge onto us, then this gets even worse. You could make the moon even more massive, and it would be causing the planet to wobble back and forth, but not forwards and away, which means that it's even harder to detect via radial velocities. So just to kind of summarize that, radial velocities perform worse for low mass objects, like we would expect moons to be. They perform worse for objects in face-on orbits, which we would also expect moons to be, actually. And that's just because of the way we think moons form. They probably form out of the same disk of material as the planets form out of, which means that they'd be most likely to be on orbits that are in that same plane. Which isn't the edge on orbit that we need in order to detect them via RVs. And finally, radial velocities are hard to do for dim primaries. And the primary is the object that the light is actually coming from. So in that case, this would be the planets. And those planets are dim compared to a star, which makes it harder to observe their radial velocities. And then finally, I just want to add that direct imaging as a method is still kind of hard to do. It's difficult technically to block the light from that star and observe those planets to get spectra from them. Okay, so next I want to talk about exoplanetary transits. So transits are another way that we discover exoplanets pretty regularly. A lot of exoplanets have been discovered this way, mostly by the Kepler Space Telescope and soon by TESS. And what I'm showing here is a simulation of a planet and an exomoon transiting their star. So if you just had a planet, you'd just see the large dip without that little bump in it. That little bump that you're seeing is what happens, you can see in the animation above, when the moon transits the planet. And so at that point, you're not blocking quite as much light from the star. So what you're seeing on the bottom is actually the brightness of the star over time. And when the planet moves in front of the star, it blocks some of the light. And so that's why you see that dip. So when the moon is in front of the planet, when they're overlapping like that, you're not blocking as much light. And so you see a little bit of a rise in brightness for that moment. Now, this is only one thing that one way that a exomoon transit can appear. You can have a lot of different geometries for these things. So you could have, for instance, a situation where the moon never overlapped the planet, in which case you'd just see kind of a double dip, a double transit superimposed on top of each other. You could also have a scenario where the moon is so distantly separated from the planet that they don't even transit at the same time, in which case you'd see two of these transit dips sort of next to each other. But I'm just using this as an example for now. And what I've given you here for an example, because I wanted you to see the signal from the exomoon, this is kind of an ideal case. This is like I don't know, maybe a Neptune-sized moon orbiting a Jupiter-sized planet. So you see this really big signal. And I've also shown you this signal with no noise at all. So this is if the star was perfectly stable and you had a perfect telescope and you could measure exactly how bright the star was. In reality, this is sort of a more likely scenario for the sizes of these things. So this is something like a Mars-sized moon around a Jupiter-sized planet. And you can see that that signal we saw before is now really, really tiny. And this is still a simulation without any noise. So these small signals, if you add noise into this, because stars aren't perfectly the same brightness all the time, and our telescopes aren't perfect. And if you're looking from the ground, the atmosphere is not perfect. And all of that adds noise to this light curve. And that easily swamps a signal of this size. So that's why Kepler, in all its time staring at these stars, it never had an unambiguous detection of an exomoon. And I'll explain in a minute why I say unambiguous. The picture I'm showing on the right here is Kepler's field of view on the sky. That's not particularly important to what I'm saying. I just like that better than a picture of the telescope. TESS is currently searching for exoplanets, and I have its field of view on the sky here. This is actually a lot of fields of view. So TESS tiles its way around the sky. On the left, it's observed most of the northern hemisphere of the sky. And on the right, that's showing the sky's southern hemisphere that it's working on now. So it's observing a lot more stars than Kepler because it's looking almost every direction. But it's a little bit less sensitive than Kepler is, which means that it's unlikely, since Kepler didn't detect any exomoons, it's unlikely that TESS will. All right, so I said a minute ago that Kepler didn't have any unambiguous detections of exomoons, but there is an ambiguous detection of an exomoon candidate. We say it's a candidate because it wasn't able to be statistically vetted, which is the process by which we decide that a planet is a confirmed planet rather than a candidate. So in this case, we call this an exomoon candidate. On the right-hand side here, you're seeing the Kepler data. And this is work by Alex Tichy. He, along with David Kipping, fit exomoon plus planet models to the data for this star that came down from Kepler. And they think that they saw a exomoon here, or at least they saw an interesting enough signal. So you can see these models. The small dip is the exomoon and the large dip is the planet. I think if you look at the actual data points, the actual flux from the star over time, that's these gray points with the error bars on it, it's maybe a little bit hard. The models are suggestive and help, you can kind of use those to lead your eye to see the potential signal, but it's a little bit hard to see anything there if you don't have these models to sort of lead your eye. I think maybe the third transit here is where you can see it most clearly what they're looking at. The moon ends up in a different place in each of these three transits because the moon is orbiting the planet. So it always ends up in a different location when the planet transits the star. So that's why these all look a little bit different, but it's the same moon. So they thought they saw something there, and the people at Hubble agreed that it was good enough for them to get time on the Hubble Space Telescope to look for this moon. And this is showing the data from the Hubble Space Telescope and their best fit exomoon plus exoplanet model. And here the exomoon transit shows up at the very edge of the data, which is kind of unfortunate because you don't have the other side of that transit, which makes it hard to say for sure that that's actually a transit shape, because we don't know off the end of this time series here, we don't know if the flux goes back up to level like you would expect for a transit, or if it does something else entirely. So for that and a few other reasons, this remains a candidate rather than a confirmed detection. All right, so now I want to talk about microlensing. And microlensing is what happens when so you're observing a star somewhere usually towards the center of the galaxy, because there's a lot of bright stars there. And what happens is that if a star in the foreground between us and that background star passes in front of the background star, we call the background star the source and the foreground star the lens, it'll actually bend the light rays from that background star under the influence of its gravity. It'll bend the light rays around that star and refocus them. And if they happen to refocus on the Earth, if we're in just the right spot with just the right geometry to see this, then we know that a star passed in front of that background source star. And if that lensing star in the foreground has a planet around it, then we see, not only do we see the increase in brightness from that background, from the foreground star, but we also see a little bump there, another little increase in brightness, a spike from the planet, which is doing its own lensing. if there's a exomoon around this planet, then you can see even an additional little bump from the moon lensing light and focusing it on the Earth. Now, this method in principle actually could detect something the size of an exomoon, but there's kind of a fundamental issue with actually saying for certain that anything you've detected is an exomoon. And that's that what you get from microlensing is a snapshot of this system in time. So I've given you this is just a little diagram that I drew. This is kind of this isn't, you don't actually literally see this when you observe a microlensing event, but this is kind of what you can reconstruct from the microlensing event. The dashed line here is the background star that's being lensed. In the foreground, I have the star that's doing the lensing, which is accompanied by a planet and something that may or may not be a moon. And so what you get is kind of a snapshot where you see the relative positions of these objects at the time when the lensing event happens. But you don't get, so you're seeing a projected view of this. You don't have any three-dimensional information about what's happening in this system, which means that you can't tell whether that smaller object is actually orbiting the planet or if it's maybe just another planet in the background. So to illustrate this, I've drawn two diagrams here, which would look the same if you saw these systems microlens a background star. So if you're the observer off the bottom of this slide and you're looking up at the system on the left where you have an exomoon orbiting a planet, you just see two objects that are near each other off to the trailing end of the star that does the lensing. On the right here, I have a system that would look in microlensing exactly the same, except this isn't a moon at all in this case. This is another planet orbiting closer to the star. And it just happens to, from the angle you're looking at, be lined up. So you might be able to see an exomoon in microlensing, but you would never know if it's actually a moon or not. And there's an additional problem here, which is that you can't actually go back and observe these systems again for most microlensing events, because very often the star that actually hosts the planets is too dim or too far away to be able to use any of the other methods of observing exoplanets that we have. And that microlensing event is just a chance event. It's a 1 in a million thing. We only observe these at all because there's so many stars moving around in the galaxy. But for a single star, this is a 1 in a million thing. We're never going to observe this microlensing event again. The star is probably too dim to observe in any other way. So we never get to go back and look at this system to confirm whether this was an exomoon or a planet. And so those are some of the reasons that we haven't detected any exomoons yet. Those are some of the difficulties that we have in observing these systems and in observing something as small as an exomoon. So now I want to talk about how in the future, I think we might be able to detect exomoons. And the first thing that I want to talk about is an upcoming a new type of telescope, a few of which are being built currently. So we call these extremely large telescopes, which is a very descriptive name, but that's also sort of the technical name for these things. What I'm showing you here is a rendering of the Giant Magellan Telescope, which will be built in Chile. And this is a rendering of the Extremely Large Telescope, which will be built by Europe and also in Chile. And both of these will have, in addition to the ability to directly detect exoplanets, like HR 8799, like that system that I talked about at the beginning of this presentation, they'll also have new radial velocity instruments that'll do a much, much more precise job of measuring radial velocities in these systems than anything that we currently have. So with these new telescopes and the new instruments on these telescopes, we'll be able to use that combined radial velocity direct imaging method much, much better than we're able to now. So that sort of proof of concept thing that I showed you before, we'll be able to do that much better and put much, much stronger constraints on the very least at the kind of exoplanets that could exist in these systems. So that's one possible path towards exomoon detection. Another, back to microlensing, another is the Roman Space Telescope. The Nancy Grace Roman Space Telescope is supposed to be launched sometime in the next decade. I'm not sure of the exact date. And from experience with JWST, I don't know that it makes any sense to tell you that it'll be launched in a specific year or even a specific decade. But 2025, okay. Oh, and I accidentally went forward there. Hold on, let me back out of this and find my, oh no, I'm going the wrong direction. Okay. 2025, Heidi says, is when this will be launched. This telescope is mainly intended to do cosmology work, but it's also expected to discover a lot of microlensing systems. So what I have over here on the right is a plot from a paper by Penny et al. In 2018 showing the expected yield of microlensed planets for the Roman Space Telescope. On the x-axis, we have the planetary mass in Earth masses on a log scale. On the y-axis is the semi-major axis, so the distance from the star in units of the Earth to Sun distance. Now, one important thing that I haven't mentioned yet is that if we're looking for exomoons, we're interested mostly in planets that are orbiting at a large distance from their star. Close-in planets are not a great place to look for exomoons, and that's because for close-in planets, the star's gravitational influence is a little bit too strong. And we expect that exomoons around these close-in planets will be potentially pulled away from their planets by the star's gravity. And they'll end up either as free-floating planets of their own, or they might be thrown out of the system, or through complicated gravitational interactions, they might be pushed into the planet. So we don't expect those kinds of moons to survive very long. So we want to look at planets that are further away from their star, like the Earth's distance or more. And so what you notice immediately from this plot is that they have the Kepler detections in red here. All of these Kepler detections are relatively close into their stars. So while Kepler did get down to sort of the range and radius that we might expect exomoons to be, all of those planets are really, really close to their star where we wouldn't expect exomoons to be able to survive for very long. So what's nice about WFIRST and it's the detections that it's expected to make is that all of these microlens planets are expected to be at large orbital separations where we think exomoons can persist for longer, where they'll be more stable. And in addition to that, you can see by this curve, this blue curve is sort of showing you a rough estimate of the detection limit. This goes down to very, very small masses. Here we're talking about masses rather than radii. But this goes down to very, very small masses. This here is the mass of Ganymede, Jupiter's most massive moon. So we certainly expect that we should be able to see things the size of exomoons. We're out in the region of space far away from the star, where we would expect to see exomoons. There's still the issue of saying for certain that anything we observe is an exomoon. But my hope would be that if you see lots and lots of microlensing events with this telescope, then at some point you can start to say that the probability of seeing pairs of planets that close to each other over and over again becomes very small. So while you might not be able to say for certain that we see this exomoon, you might be able to get a handle on kind of the population of exomoons by thinking about how many more of these sort of pairs of planets do we see than we would expect to see by chance. All right, so now I want to talk about transits, which are sort of my favorite method of exoplanet detection. This is something that I've worked on a lot more. And I think there's a good reason to think that we might be able to detect transiting exomoons in the future. Now I'm going to start here by talking about James Webb briefly. And actually, James Webb, I don't think is going to be our best option for detecting, sorry, JWST, I prefer to call it. JWST, I don't think is going to be our best option for detecting exomoons, not because it can't see them. It's sensitive enough. It does better than Kepler. It has, so Kepler and TESS look just in one filter. They only see one color of light. JWST will cover a large part of the spectrum of light, of the infrared portion of the spectrum, which is very valuable information for detecting exomoons, which I'll explain more of in a bit. So it's good from that perspective. The problem is that JWST has a fairly short mission lifespan, and a lot of people want to use it for a lot of things. And so I think that trying to get time on this telescope to search for exomoons is it's not likely to happen. And in fact, I submitted a proposal to do that and it was rejected. And I probably won't submit another because it was a fun little practice proposal, but I don't think that there's a lot of interest in doing that kind of work with JWST. But there are other options in the near future. And one of those is Plato. This is a European mission that, much like Kepler and TESS, will stare with an array of telescopes at the sky and measure the brightness of stars over time and look for those dips that are caused by transiting planets. This is a really cool graphic that the Plato people put together. And there's a couple reasons why I think this is a really promising mission. More promising than Kepler and TESS, even though it's doing kind of the same thing. And that's that Plato has a signal to noise that is comparable to Kepler. So that's kind of how we talk about the sensitivity of the telescope. So it's similar to Kepler in that way, a little bit better than TESS, but it's focused on brighter stars than Kepler focused on. And brighter stars, when you give off more light, we get more information from that star, and more information means that we can also have greater precision in our analysis. So that's a good thing that it focuses on brighter stars. And then finally, I alluded to this with JWST, but Plato has two color filters. So rather than just looking in one filter, like Kepler and TESS have done, Plato has two filters, which is helpful for removing the effects of stellar variability, which can make it difficult to detect exomoons, and also for discriminating between false positive scenarios. A false positive is when we see something that looks like a signal of an exomoon or an exoplanet or whatever we're searching for, but is actually caused by a different phenomenon. So I'll talk about that in a little more detail now. So these are the benefits of multi-wavelength observations. What I'm showing here is an animation from a solar telescope in Hawaii of a close-up of the sun. And what you're seeing is, over a period of time of, I guess, looking at the corner of the animation here, it looks like that's actually only a period of time of a few minutes. You're seeing granules on the surface of the sun evolving in time. So the bright areas are hot material that's coming up from the interior of the sun. And then that material cools and falls back into the star. And that's where you see the dark edges of these granules. And so you can see, looking at this, that this is a very time variable phenomenon, that this picture is always evolving. And that means that the light that we get from the star is always changing. It's also always evolving. And so this is a source of stellar variability. There are other sources of stellar variability, but this granulation noise in particular is really important on the timescale of transits. And you can see this in this plot by Kiyavasa et al., which shows the effect of this granulation on a simulated transit of an Earth-sized, or a terrestrial at least, exoplanet in front of a star showing that kind of granulation. And what they've done here is they've simulated this transit, I think 42 times is what's in the paper. And they've taken sort of the highest or the deepest transit and the most shallow transit from those 42 simulations, all with a planet of exactly the same radius, and plotted those here to sort of show you the uncertainty that results from that granulation. Now, this might not look like a lot of uncertainty in the depth of the transit, but this gets more and more important as the transiting object becomes smaller and smaller. So when you're talking about a moon that maybe only has a depth that's about as deep as the width of this uncertainty, then suddenly that amount of uncertainty is the difference between detecting or not detecting the moon. So what I have here is actually a light curve from the sun split up into 3 bands, so that you can see this variability. And what I want to note is the wavelength dependence of this variability. So in the in the top here, we have the red filter. This is data from the SOHO spacecraft. In the top is the red filter, and then we move to shorter wavelengths, a green filter and a blue filter. And we have the same, if you kind of look real close or maybe squint a little bit, we have the same kind of variability. You see bumps in the same spot. So when the star gets a little bit brighter, it gets brighter in all of these bands. But the amplitude of that variability changes as you go from longer wavelengths to shorter wavelengths. You see much more variability in the blue filter than in the red, for instance. And that's a result of the fact that this is a temperature-dependent phenomenon. So you saw when I showed you the granules, they had hot centers and cool outer edges. And those different temperature components have different spectra associated with them, which means that the variability also has a spectral dependence. And so what we can do with that is we can use that information to do a better job of measuring the parameters of transits. And that's what I'd like to show you here. So this is a plot from a paper of mine. On the right, I'm showing a simulated transit in 2 bands with some amount of variability of the type that I've been talking about. And on the left, I have the results of doing inference on that data. The gray here is what I get from doing this inference procedure on a monochromatic light curve, monochromatic meaning single filter, where I've taken these exact 2 light curves and I've combined them to get rid of the spectral information. So I'm just looking at 1 light curve, and I'm trying to measure the parameters of this transit from that 1 light curve. So that's in the gray lines, and the colored lines are the results of that inference on the version of this data where I've separated it out into 2 filters. And so what you're seeing here is this is a graphic sort of showing the uncertainty in these measurements. So T naught is the time at which the transit occurs. So that's the center of transit. The true value represented by this dashed line is 0 days, just kind of arbitrary. Delta is the duration of the transit, and RP is the radius of the planet that caused this transit. And so in the colored lines here are showing you the probability of the parameter having a specific value as a function of the value of that parameter. And so the thinner the spike, the more certain we are of that value. And so you can see that when we go from doing the monochromatic inference to separating this out into 2 separate bands, we can find with much smaller uncertainty the values of these parameters. And we also do a better job of actually locating the value of those parameters. And so, this for planets, this means that we can measure with more precision the parameters of the transit. For moons, this might mean the difference between detecting them at all or not seeing them. Let's see. So this is something that Plato has the capability to do, at least to some extent. The caveat being that the instrument hasn't been built yet, so we don't really know anything about the characteristics of the instrument, how sensitive it'll be, what exactly these bands will be like. But the fact that it has multiple bands means that there's some hope of being able to do an analysis like this. And finally, I want to talk a little bit about false positives. And the false positive that I'm going to talk about here is star spot crossings. So on the left, I have a plot from Brett Morris's 2017 paper showing the star is called HAP-P11, and it's orbited by a giant planet, and the star has a lot of spots on it. And when the planet crosses or transits over one of those spots, because the spot is dimmer than the rest of the surface of the star, then the planet at that moment is not blocking as much light because it's covering a dimmer portion of the star. So you see a little bump in the transit curve. On the right here, I have a simulated exomoon transit. I didn't even this is not like a fit to the data on the left. I just played around and tried to find parameters that caused a transit that looked sort of the same. This is a simulated exomoon transit. And I think just looking at this, you can tell that these signals are a little bit hard to distinguish between. If this is a star spot crossing and you observe this, you're likely to say that this is a star spot crossing as well, rather than attributing that to an exomoon. And if you want to claim that it's an exomoon, you're going to have to demonstrate that it's not a spot crossing. But fortunately, and I don't have a simulation of this, so I'll just talk you through it. Fortunately, star spots also have wavelength dependence, because again, it's a temperature dependent phenomenon. So the star spot has a different spectrum than the rest of the star does. And so when you're crossing a star spot, this bump that you see here would look different if you observe this in two different bands, two different color filters. It would look different in those filters. It would have a different height. That's not true for an exomoon transit signal. And that's because the exomoon blocks the same amount of light no matter what the wavelength is. So no matter what band you look in, you'll always see a feature with the same height. So that means that if you have two different color bands that you can look in, you can tell whether you're looking at a star spot crossing or an exomoon transit. So that's a way that having that additional information that you could get from something like Plato or JWST, if it actually observed an exomoon, gives you the ability to avoid false positives. And with that, I just want to jump to my summary slide. So exomoons are challenging to detect, but I would argue that they're definitely worth the effort. If the JWST time allocation committee disagrees with me, that's fine. In the near future, I think that ground-based instruments as well as space-based observatories will be able to detect large exomoons if that population of exomoons exists. The Plato spacecraft, the Roman Space Telescope, and extremely large telescopes, I think, are some of the best bets in the near future for detecting exomoons. But even so, detecting these objects is going to require a really careful analysis of the data that we get from these instruments, because we're going to have to push to the very limits of their abilities in order to detect these objects. And that's it. That's my talk.
Great. Thank you so much, Tyler. It's really interesting, and your work is really impressive.
Thank you.
Let me use my host privilege to ask the first question, if you don't mind.
All right.
So Plato has two bands, but why stop at two? Is it really expensive to add a third or fourth?
That's a really good question, and I don't know the answer to that at all. I think the answer is probably that it costs you some amount of weight, since you're launching these things to space, to make the optics more complicated. Also, I think that anytime you're splitting the light into multiple bands, into multiple filters, that probably entails losing some amount of information in that process. So I think that when they built Kepler, for instance, I think it was probably a design decision to really optimize it for taking in as many photons as possible in one band, and measuring really precisely the brightness of the star in that way. That's my best guess.
That might be why Roman and JWST are not optimized for this kind of detection, because just the light are spread into too many bands.
Yeah, I think so, because interesting enough, JWST, for instance, I've done a little bit of work simulating these kinds of exomoon observations with JWST, and it is not it's not much better than Kepler when you add all of the light together across the spectrum. It's not that much more sensitive than Kepler was. It has a lot of capabilities that Kepler didn't have that make it really great for a lot of other things, especially spectral observations. But for doing this kind of work, it's actually in a lot of ways not particularly optimal. Yeah.
I see. Cool. So we have a question from YouTube. And what is the extremely large telescope that you showed? Where is the extremely large telescope that you showed?
Where is it?
Yeah.
So that's also being built in Chile. So that's a telescope project by the European Southern Observatory. Somewhere in the Atacama Desert of Chile. I don't know exactly where. I've never been down there, but in the Atacama Desert, you have really, really high mountains and a really, really dry atmosphere. So it's one of the best places in the world to put a telescope. And so that's why all of these extremely large telescope projects end up there. Or in, Hawaii's another scientifically a very good spot to put a telescope. I think ethically not a very good spot to put a telescope. Other places in the world, there's the Canary Islands off the coast of Africa are a really good place to put a telescope for the same reason. You have a very high mountain and dry weather, which makes it easier to see through the atmosphere.
Can you hear me now?
Yes.
Oh, great.
Yeah.
Okay. We're sitting here trying to talk. Yeah, that was great, Tyler. Let's give a round of applause because I think Tyler came over here. It's okay.
Good to have a little feedback.
People here were eagerly listening, hanging on your every word. You just couldn't hear any of it. That was just excellent. Really great. Any questions in the room here? Yeah, I'm going to bring the mic over, okay? We'll give you that chance. Here you go.
I'm just wondering about the density of the exoplanets. How much difference is that going to make?
Yeah, that's a good question. So that depends very much on the detection technique, I suppose. So if you're observing transits, it doesn't matter much how dense the planet is. It just matters how large its radius is, because it's the size of the planet that blocks the light. So transits are what I think a lot about. Density is not so important for detectability there. Now, if you're looking at something like microlensing events, then the mass of the planet is what determines how much it's able to bend that light. So in that sense, density becomes important. The same for radial velocities. The mass of the planet is what's important there. I guess other ways in which density are important, you could talk about we think a lot about like stability of exomoons around different planets, and parameters like the density play a role in whether we think that an exomoon is stable over long periods of time or not. So sometimes considerations like density matter there. Largely for what I'm interested in, I just want to see the things. Characterizing them comes next, I think. So on that level, density doesn't play a huge role for me personally. Yeah.
Excellent. Other questions? Oh yeah, for sure. Hang on one second.
Hi, Tyler. So let's see. So we have three techniques for chasing exoplanets, and all of them are limited by the quality of the data coming in from the hardware, but they're also limited by your ability to analyze it and cut the noise. Which will win the race? Will it be the better analysis or the better hardware?
Yeah, that's also a really good question. I think that I think that both are absolutely essential. So on some level, I think we're at a place with like exomoons right now where there's some fundamental limitations on what we can do with the data that we have. I think we can do the most sophisticated analysis in the world, but if we don't have precise enough observations, if we don't have the right kinds of observations, so I keep going on about having observations in multiple bands. So the kind of analysis that I'm interested in doing can't be done with data only in a single band. And so I think in that sense, I think right now our ability to detect these things is probably held back by the availability of high quality data. Not to say that we don't have high quality data. We have really high quality data. It's just that exomoons are a really hard thing to detect. So yeah, I think on some level we need the hardware we need good enough hardware to be able to actually do this work. I think the theory, the data analysis is ready to go.
Okay, maybe let me ask one. Do people talk about exoplanet rings? Are they ever possible to detect?
Sorry, could you say that again?
Do people ever talk about exoplanet rings, like Saturn rings?
Hey, sorry, we had a question here in the room. I apologize. I was on mute. Let me get that question in, and Heidi, then let's definitely have your question about rings. Give me
Okay,
1 second. Let me
sorry.
try this again, Tyler. Sorry. Okay, here you go.
Okay, Tyler, it seems to me that the orientation of the exoplanet orbits and moons orbits really plays a big portion of how well we can detect them. Do we have any kind of statistical analysis of those orientations across all the systems that we've seen?
Yeah, so you're absolutely right. The orientation plays a huge role. Several of these methods are sort of dependent on having a favorable geometry. And yeah, we do have a statistical analysis of that. So I think this will answer your question. One major goal of exoplanet science is to understand, from the limited observations that we have, we want to understand what the total population of unseen planets and, you know, someday potentially moons looks like. And so that requires understanding what the biases are in what you're able to see. So with transits, for instance, we can only see these systems that are edge onto us so that the planet actually transits. For radial velocity, the planet has to be edge on enough that it actually causes variations in radial motion of the star that we're able to see. So if you understand all those biases really well, you can kind of back out what you expect the population of planets that you don't see to be. And so that's a really important line of work. And there's been a lot of good work on that, on exoplanet population statistics. Yeah. Should I go ahead and answer Heidi's question about rings? Because I think that's a good one too.
Please answer that one.
Okay, so rings are absolutely something that people think about, and in a lot of cases they go kind of right along with exomoons. I think some of the challenges are similar. They cause like similarly small signals, and so detecting rings of exoplanetary systems is also something that people who think about moons think about a lot. And I've thought about it a little bit. I think I included something about rings in my JWST proposal, just to, you know, expand the range of things that we might have been able to observe under that proposal. Yeah, just like exomoons, they're a small signal close to the planet, probably detectable via transits. In the future, obviously, something like radial velocity doesn't really give you any information about rings because their mass just gets folded into the mass of the planet. The same with microlensing. But yeah, definitely something that people think about.
Great, thanks.
Really, really great questions. I'm going to go ahead and let's go ahead and wrap it up here since it's getting very late. Let's give Tyler another round of applause here in the room. I hope you can hear that, Tyler.
A little bit.
So, yeah, really excellent talk. Folks really enjoyed it. Those of you on YouTube, thanks so much for joining us. We're hoping to be able to host these again in person in the spring. So stay tuned for information about that. Those of you in the room, thanks very much for joining us. These First Friday events are entirely donor supported. The school does not provide any money for this at all. So this is something you want to see more of. Please consider supporting us. There's information about how to do that outside. Everyone have a great weekend. Stay safe, stay warm. We'll see you in January.